Okay, so we're going to explore an alternative version of the quadratic formula that looks a little bit different to the familiar form of the quadratic formula that we know. So we'll start by deriving this and seeing how it's related to the original quadratic formula. Then we'll explore some advantages and disadvantages of each different formulation. So to derive this, we're trying to solve the equation ax squared plus bx plus c equals 0. And now to get this alternative version of the quadratic formula, the first step is we just divide through by x squared. So this is going to be fine as long as x isn't equal to 0, and we will address this point later on, what happens when x is 0, but dividing through now by x squared, we get ax squared dividing by x squared gives us a, b times x divided by x squared gives us b times 1 over x, and c divided by x squared gives us c times 1 over x all squared, and this is still equal to 0. So now we can see that this is actually a quadratic in the variable 1 over x. So let's just rewrite this as c times 1 over x all squared plus b times 1 over x plus a equals 0. Then we could actually solve this for the variable 1 over x using the original quadratic formula. So this would give us 1 over x would be our minus b, the coefficient of our variable there is still actually just minus b, so the role of b hasn't changed there. And then we've got plus or minus the square root of b squared, so again b has stayed the same, but now our a and c have effectively swapped here. But because we're doing 4 times a times c, if we do 4 times c times a, we still get the same number. So we can still write this as b squared minus 4ac. And the only big difference here is now instead of dividing by 2a, a is our coefficient of our variable squared, so this is turned into a c here, so we need to divide by 2c. So this gives us expressions for 1 over x, and then we can just take reciprocals here to get our solution x. So taking reciprocals, we see that x is going to be 2c over minus b plus or minus the square root of b squared minus 4ac. So this is actually our new formulation of the quadratic formula. So I'll have a look now at how this is related to the original quadratic formula before exploring some advantages and disadvantages of each different formulation. And we can see how these are related to each other by applying a process similar to rationalising the denominator, only for the direction we're interested in here, we're actually going to be rationalising the numerator. So if we wanted to rationalise the numerator in this expression, we would just multiply by the conjugate. So we would multiply by minus b, then just to avoid doing this in two separate cases for the plus and minus, this becomes minus plus the square root of b squared minus 4ac. And we just multiply by this on the top and bottom of our fraction, so we haven't changed the value of anything. So then the whole point of doing this is so that in the numerator we get a difference of two squares expression. So minus b times minus b gives us b squared, then we've got plus minus times minus plus the square root term. So we just do the square of the square root term, so we end up with minus b squared minus 4ac like this. And in the denominator we'll do 2a times minus b, so minus 2ab, then minus plus 2a times the square root of b squared minus 4ac. Then you can see in the numerator our b squareds are going to cancel, so b squared and b squared cancel, and that leaves us just in the numerator then with 4ac, and then the denominator it's minus 2ab minus plus 2a times the square root of b squared minus 4ac. So then here we can take out a factor of 2a from everything. So if we just divide through by 2a here, here and here, this 4a just turns into a 2. Then you see that we get 2c in the numerator, and our denominator simplifies now to just minus b minus plus the square root of b squared minus 4ac. And this is our solution for x expressed in this rationalised numerator form now, but because we've got the minus plus, this is just saying these are our two solutions where we add or subtract the square root. So then we can just write this minus plus as plus or minus then. So we end up with 2c over minus b plus or minus the square root of b squared minus 4ac, exactly like we had before. So now we can see how these two expressions are actually just very much the same thing, just one has a rational numerator and the other has a rational denominator. And now we're ready to explore some advantages and disadvantages of each different version. So we start with the original quadratic formula. The problem here is that it's not actually well defined when a is equal to 0, because we end up dividing by 0. But in the case where a is 0, our quadratic equation can actually have solutions. So it just reduces to bx plus c equals 0. And in general, we should be able to get a solution minus c over b, but the original quadratic formula misses this solution. So let's see what happens if we substitute in where a is 0 into our new quadratic formula. We'd get x would be 2c over minus b plus or minus the square root of b squared. So the 4ac term just disappears because a is 0. So here the square root of b squared isn't just b. We get something slightly different if b is negative. The square root of b squared would be the positive version of b. So if we just consider first of all where b is positive, so here the square root of b squared is b, so we get 2c over minus b plus or minus b. So then this gives us our first solution where we have minus b plus b in the denominator. We end up with 2c divided by 0. And our second solution would have 2c over minus b. So this gives us 2c over minus 2b, which simplifies to minus c over b. So you can see here the 2c over 0 solution doesn't work, but we do retrieve this minus c over b solution to our quadratic equation where a is 0. This is in the case where b is positive. And similarly, when b is negative, we'd have 2c over minus b plus or minus the square root of b squared. But here, the whole point of splitting this up into positive and negative b is that the square root of b squared is actually the negative of b when b is negative, so it needs to be a positive answer for the square root. But then we're just adding and subtracting minus b, so we actually get the same two solutions. When we do minus b minus b, this gives us 0 again. So we get the same two solutions, 2c over 0, and we get 2c over minus 2b for minus b plus minus b in the denominator, which again simplifies to minus c over b. You can see that the division by 0 doesn't work, but we do again retrieve this minus c over b solution in either case. So we can actually say then when a is 0, the new quadratic formula still catches this solution, whereas the original quadratic formula doesn't. So this is a really big advantage then, that it works when a is 0. However, there are cases where the new quadratic formula doesn't work, so you can see that this won't work when the denominator is equal to 0, the formula would break down. But it's not immediately obvious which values of a, b and c would cause the denominator to be 0. So if we just set this minus b plus or minus root b squared minus 4ac, set this equal to 0, then we can add b on both sides. We see that plus or minus root b squared minus 4ac is equal to b when the denominator is 0. So then we can square both sides to see that we get just b squared minus 4ac on its own on the left is now equal to b squared in this problematic case where we have the division by 0. So then the b squareds cancel. We see that this is problematic exactly when 4ac is equal to 0. So this corresponds to either a equals 0 or c equals 0, or perhaps both. So we've already covered the case where a equals 0, and we've seen that actually this new quadratic formula does give us all of the solutions to our equation, generally speaking, because there's only one solution when a is 0. However, we do need to explore this case a bit more where c is equal to 0. So you can see when c equals 0, our quadratic equation becomes ax squared plus bx equals 0, and we can actually solve this just by factorisation as x times ax plus b equals 0. So we get two solutions, x equals 0 and x equals minus b over a. And at this point we'll just point out as well that if you remember in the derivation of the new quadratic formula there was an issue where x couldn't be equal to 0. So this actually corresponds to the case where if x equals 0 as a solution, this happens if and only if c equals 0. So we're covering this case where x is 0, which seemed to be problematic for our new quadratic formula, by considering this case where c equals 0 now. So if we were to substitute in a, b and 0 into the original quadratic formula, you can check that you would indeed get x equals 0 and x equals minus b over a, as long as a wasn't equal to 0. So we capture both of these solutions with the original quadratic formula. So now let's try substituting in c equals 0 into the new quadratic formula, see what happens. So we'd have 2c over minus b plus or minus the square root of b squared minus 4ac. This would give us 0 for our 2c, because c is 0, over minus b plus or minus the square root of b squared, because the c is equal to 0, so our 4ac disappears. So we're in this situation again where the square root of b squared is either b or perhaps the negative of b if b is negative. But either way, we're just adding b and subtracting b for our two solutions. We get 0 over minus 2b for the case where it's minus b, take away b. And then we get our other solution would be 0 over minus b minus minus b. So it would be 0 over 0. So here, as long as b isn't equal to 0, we would actually get the solution x equals 0 from 0 over minus 2b. But this one, 0 over 0, definitely isn't well defined. So here we miss out on the solution x equals minus b over a with our new quadratic formula. So the conclusion we could draw here is actually that if you're in a situation where maybe your a, b and c are varying, so if your a varies and could be possibly equal to 0, you might want to consider using the new quadratic formula. Whereas if you're in a situation where c varies and c could be equal to 0, you're probably better off sticking with the original quadratic formula in that case. And now we'll finish by comparing the accuracy of each formula if we have to use some rounding in our calculations. So if we consider this example where we've got a is a half, b is minus 8 and c is 2, let's just substitute these values of a, b and c into each quadratic formula. So for the original quadratic formula, you can check that we're going to get 8 plus or minus the square root of 60 just divided by 1. And it's this step where we need to calculate root 60 that we would need to use some rounding if we were doing this by a computer. So root 60, this is approximately, let's just round this to one decimal place, 7.7. So this would give us, for our two solutions then, we've got around 15.7 and 0.3 using the original quadratic formula. So now if we look at this for the alternative quadratic formula, again substituting in our values of a, b and c, we'll get 4 over 8 plus or minus root 60. So now this root 60, if we again approximate this by saying this is around 7.7, let's see what this gives us in terms of our two solutions from this quadratic formula. We'd have 4 over 15.7 for one of our solutions, and our other one would be 4 over 0.3, where we do 8 minus 7.7. Then if we actually calculate these two fractions, 4 over 15.7 gives us 0.2548 approximately, and 4 over 0.3 is going to give us 13.3 recurring, so 13.33, and so on. So what are the actual solutions to this quadratic equation? Well, if we calculate them exactly, our solutions are 0.2540 approximately, and the other one, if we calculate this exactly, it's 15.75 to 2 decimal places. So you can see here we've got a really interesting set of results, that our original quadratic formula gave us a really good approximation of 15.7 for our big root, 15.75, but the 0.3 isn't as good compared to this 0.2540 that it should be, especially proportionally we're off by almost a fifth of the entire root. And then if we look at the alternative quadratic formula, we get the opposite behaviour, that we have a really bad approximation for our big root, but then for our small root, 0.2540, we've got 0.2548, which is much closer than we had 0.3 for the approximation using the original quadratic formula. So we'll finish now by exploring and trying to understand why this has happened. It seems that the problem here was that minus b was approximately the same as root b squared minus 4ac. So to see why this causes us a problem, if we've got two quantities that are reasonably close to each other, when we find the difference between these, when we calculate minus b minus root b squared minus 4ac, this difference between two things that are very similar to each other should be very small, but then it becomes very sensitive to any sort of inaccuracies when we approximate the square root. So in our previous example we had minus b was 8, and the square root of b squared minus 4ac will be 7.75 rounded to 2 decimal places. So this should be around 0.25. So now this value for the square root of 60, we rounded this to 1 decimal place. So instead of rounding up to 7.75, this actually rounded down to 7.7. So this is where we got this approximation of 0.3. So you can see by rounding this number, because the difference between the two numbers is only very small to begin with, we get this really big proportional change from around 0.25 to 0.3. So this is saying then that minus b minus the square root of b squared minus 4ac isn't going to be very reliable to use, and we want to actually try and avoid that. So this is where we can take advantage of actually having two different quadratic formulas now. So the two quadratic formulas give us two different expressions for each of the roots. So our first original quadratic formula, we have minus b plus root b squared minus 4ac all over 2a, and we've got the same with the minus square root of b squared minus 4ac over 2a. So what we've just learnt here is that minus b minus the square root should be avoided because this gives us a really bad proportional error. So if we avoid using this one, we can instead use the corresponding solution from the alternative quadratic formula. So here, when we have minus b plus the square root, it turns out that this is actually equivalent to, in the alternative formulation, the calculation where we'd have minus b minus the square root. So this one corresponds to 2c over minus b minus the square root of b squared minus 4ac. So when we rationalise the denominator, or go in the other direction, rationalise the numerator, you see that these two are actually equal to each other. And similarly, this one where we have minus b minus the square root in the numerator, this is equivalent to having 2c over minus b plus the square root of b squared minus 4ac in the denominator there. So you can see that these two are actually equal to each other as well. So here we want to avoid using minus b minus the square root term, just because we know that in a proportional sense this is quite a bad approximation. So we can use minus b plus the square root, because here with this approximation it just doesn't give us as much of a problem in a proportional sense. So here 8 plus 7.75 will give us 15.75, and here 8 plus 7.7 still gives us 15.7. So even though they're off by the same amount from each other, in a proportional sense this isn't a problem. So then when we take the reciprocal of this, this is why we get a slightly better approximation using the new quadratic formula for our smaller root of this equation, whereas we got a better approximation from the original quadratic formula for our larger root. So I think it's really interesting to conclude here then that there are some examples. If your minus b is approximately the same, or it's very close to your root b squared minus 4ac, it could even make sense to use one quadratic formula for one of the roots and use the other quadratic formula to find an approximation for the other root.